Welcome back, ladies and gentlemen. Today, we're going to be looking at area. And you've all taken a geometry course, and you know how to find the area of polygons and circles. But what about non-regular shapes, like, for instance, this parabola that I have shown here? Well, the best we can do is we could approximate this area. We could come in here and say, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and you get the idea. We could count the number of boxes and approximate how many square boxes there are underneath this curve. And that's all fine and dandy, but there's got to be a better way. We want to know exactly how much area is underneath this. So, a gentleman by the name of Riemann decided, a good way to find these areas would be by using rectangles. So he came in and he said, okay, I'm going to make a whole bunch of little rectangles. That little rectangle. We've got that little rectangle. And he split the x-axis into a bunch of evenly spaced intervals and made a rectangle that goes up to the curve for each one of these, and areas of rectangles we can find. So what the area approximation would be 1/2 times, well, this point, this side right here, that would be -1, 2, 2.5. Find the function value at -2.5, and I know the height of that rectangle. The height of this rectangle would be f of 2 plus da-da-da. And we can approximate the area in this way by drawing all of these little rectangles. And I hope that it makes sense that if we use smaller rectangles, we're going to get smaller or better and better areas for under this curve. The amount of error in this, the over-approximation, under-approximation, because this would be over-approximated, over-approximated, and so on, those things are going to get smaller if we use smaller rectangles. So it's a very crude way to do it. What can we do better? Well, it should stand to reason that we could take a limit. If we said that the area underneath this curve is going to be f of x times delta x, so height of a rectangle, width of a rectangle, and we have n of those rectangles. If we let n get really, really big, that's going to mean we're taking smaller and smaller widths. So that limit should give us the area. If we take infinitely small rectangles, we should have an exact area under the curve. And ladies and gentlemen, that has been studied and come to use the notation of a definite integral. The integral from a to b of f of x dx. So this definite integral is used to define area under a curve. We say if the integral of f exists on a to b, and f is non-negative on this interval, that's important. F is non-negative on this interval, then the area under the curve is the definite integral from a to b f of x dx. So, question is, what is the area under the curve from -3 to 2 for that function that I just showed you a second ago? But before we do that, let's formalize this idea with something known as the fundamental theorem of calculus that was formally written by a fellow by the name of Augustin Louis Cauchy. It says, if f is continuous on a to b, and capital F is an antiderivative of f on a to b, then the definite integral from a to b of f of x dx can be found by taking the antiderivative evaluated at b and subtracting the antiderivative of f evaluated at a. And it says n antiderivative because it doesn't matter what the constant of integration is, because with the subtraction here, that constant of integration evaluated at b and the constant of integration evaluated at a, those will cancel out. So this theorem is important because it very clearly and formally relates the two branches of calculus, differential calculus and integral calculus. Differential calculus was traditionally all about finding velocities and accelerations. Integral calculus was all about finding areas under the curve. This theorem unified the two and allowed us to use our integral calculus and differential calculus in harmony and recognize that one is effectively the inverse operation for the other. So back it up. What's the area under the curve for our function that we saw right here? Well, it will be the integral from -3 to 2, negative x squared minus x plus 6 dx. And how do we evaluate a definite integral? How do we take the antiderivative here? Well, we're going to increase the exponent by 1 and then divide by it. So our notation becomes -1/3 x cubed minus 1/2 x squared plus 6x. I don't need the constant of integration because when I use that fundamental theorem of calculus, that constant will go away. And we evaluate from -3 to 2. So fundamental theorem says take 1/3 times 2 cubed minus 1/2 times 2 squared plus 6 times 2. Take that and subtract that antiderivative evaluated at the lower limit. And we run this calculation, and that product is our area. And that difference is our area. So, let's practice, pause the video, and evaluate this definite integral using the fundamental theorem of calculus. You should have the antiderivative being t cubed plus 1/2 t squared, and we're evaluating at 1 and 3. We substitute our limits, and we're finding the difference between them. And now we evaluate 27 minus 9/2 minus 1 minus 1/2. We have 54/2 minus 9/2 minus 1/2, which is 44/2, or 22, as our solution to this definite integral. And here we have a bunch of properties that we actually just used in this problem, some of them. Our properties state that if we're integrating, taking a definite integral of a constant times a function, we can integrate the function and leave the constant out in front and evaluate the definite integral, then distribute. If we're taking the definite integral of a sum of two functions, we can split that into two separate definite integrals. The integral from a to a of a function is 0. Well, that should make sense because if we're talking area now, area from 1 to 1, well, there is no area between 1 and 1, so that area is 0. And here's two neat ones. Area of a to, or integral from a to b of f of x is equal to the opposite of b to a, and that's because we're switching the limits of integration. So fundamental theorem of calculus, we're interchanging the two things, we're subtracting, and when we change the order of subtraction, we get a negative of what we had before, opposite. And the integral from a to b of f of x is equal to the integral of a to c plus c to b, provided that c is in between a and b. This just says you can split a definite integral into multiple pieces as long as you're picking up where one leaves off and starts into the next one. And let's extend this area idea. Before we said that the f of x had to be positive on the interval. Well, what do we do when it's not positive? Well, when the area is not positive, when f of x is negative for all x on the interval a to b, then the area bounded by the curve, the x-axis, and the lines x equals a and x equals b is the absolute value of that definite integral, because what happens is this area is under the curve. Under the curve, the definite integral is negative, but area is measured as a positive quantity. And taking it one step further, the total area of f of x on an interval a to b, where its graph is partially above and partially below the x-axis, is a equals the definite integral from a to b of the absolute value of f of x dx. This absolute value, if you remember our study of function transformations, takes a curve that looks like this, and this part gets reflected up above, so our new function would be that, and now we're talking about all area above the x-axis, no longer dealing with that negative area below. And all that's left to do now is look at one example that ties these ideas together. So consider for a moment f of x equals this, and the expanded form would be that. Find the areas on the following intervals. Well, for something like this, it's useful to look at a sketch of it. We have x-intercepts at 1, 3, and negative 2. And this is a positive leading coefficient on the cubic, so we know that we'll start out negative, come up, down, and back up again. So find the areas on the following interval. So that would be the definite integral from negative 2 to 1 of f of x dx. That is that area. That area is above the x-axis. We don't need to worry about taking an absolute value. I'm entirely confident that we can find the antiderivative of f of x, which I have shown in green here. And this is an antiderivative, not the antiderivative. This is not, I don't have the plus c here. I didn't do an indefinite integral. I'm using this into a definite integral down here. So last thing to do would be to evaluate capital F of x at 1, evaluate at negative 2, and find the difference between them. Now, I'm going to take a technological approach to doing this. In my graphing calculator, I've graphed my function. And in my graphing calculator, I can analyze the graph and find an integral value. My lower bound, I want to be negative 2. My upper bound, I want to be 1. And there is my area, and that's the area you should have gotten evaluating this algebraically, being 7.88. Now, if I just evaluate the antiderivative, the integral, from 1 to 2, 1 to 3, sorry, it's negative 2.67. Okay, well, if I go back to this problem, if I want the area on the interval 1 to 3, that's going to be the definite integral of 1 to 3 of f of x dx. But I need to take the absolute value of that, because as we saw in the calculator, that's a negative area. So that area would be 2.67. Now for part C, we're taking the definite integral from negative 2 to 3, f of x dx. Now there's two ways to do this. If you're going to do this analytically, if you're going to do this algebraically on your paper, you would need to first find the integral from negative 2 to 1, f of x dx, and then add the absolute value, integral 1 to 3, f of x dx. With technology, we can do it in one swift swoop. We can see